All right, let's get into it. We've got a suspect. It's about 93 million miles away, weighs 2 non-million kilograms, and for well over 100 years, it's been at the center of this intense, ongoing investigation. Our suspect? The Sun. And the mystery? What in the world is going on deep inside of it that drives its rhythmic, powerful, and sometimes totally chaotic behavior?
You know, from our point of view here on Earth, the sun seems like the definition of consistency. It comes up, it goes down, it gives us the steady energy that fuels our entire planet. It just feels dependable. But that calm exterior, it's hiding a ridiculously turbulent, magnetic heart.
Because when you look closer, the sun is anything but constant. It actually breathes, with this rough 11-year cycle of activity. It swings from being really quiet to throwing these massive tantrums of solar flares and sunspots. And this cycle, it has huge effects on us. It can mess with our power grids, our satellites, you name it. So for over a century, scientists have been asking, what is the engine driving this cosmic clock? Every great investigation has to start with that first clue. And for the scientists trying to figure out the sun, that first clue was just trying to understand how a star could even have a magnetic field to begin with. So, picture this. It's 1919. A physicist named J. Larmor has this idea. And it's inspired by the cutting-edge tech of his time, the car engine. He suggested that the sun works kind of like a dynamo, that part of an engine that generates electricity. He figured that the churning, flowing motion of the sun's super-hot electrically charged gas, its plasma, could act like a giant cosmic generator, creating its very own magnetic field. This whole idea became known as dynamo theory.
Larmor's idea was brilliant, right? But it was just the starting point. It was kind of like knowing who the suspect was, but not how they were pulling off the crime. It didn't explain the 11-year cycle or why the sun's magnetic poles would just flip. For that, the investigation needed a major breakthrough.
And that breakthrough came in 1955 from a pretty young scientist named Eugene Parker. He came up with a model that, for the very first time, offered a plausible, really elegant way the sun's dynamo could not only keep itself going, but also completely reverse its polarity. He called it the alpha-omega dynamo. Okay, so this diagram here really gets to the core of Parker's genius idea. Just imagine a magnetic field line running horizontally inside the sun. As a big blob of hot plasma rises up, the sun's rotation makes it spin, kind of like a cyclone here on Earth. This spinning motion literally grabs that field line and twists it, creating a brand new vertical loop. Parker called this twisting action the alpha effect, and it was the secret ingredient, the key to creating a new magnetic field from an old one.
So how does this one little twist create a whole cycle? Well, it's like a two-step cosmic dance. First, picture the sun's main magnetic field running from its north pole to its south pole. Now, because the sun's equator spins way faster than its poles, it drags these field lines, stretching and wrapping them around its middle like a bunch of rubber bands. This creates a powerful new magnetic field running east to west. Then, and this is the magic part, that twisting alpha effect kicks in. It takes these wrapped up field lines and flips them back into a new north-south field, but with the polarity completely reversed. North becomes south. It's a self-powering cycle, and it just beautifully explained the flip.
Parker's theory was a huge win. It seemed to explain everything perfectly. But then, a new piece of evidence came in that threw the entire investigation into total chaos.
For decades, everybody just assumed the sun rotated in a really simple way, on these neat concentric cylinders. But then, in the 1990s, this amazing new technology called helioseismology let scientists basically listen to sound waves moving through the sun, and it revealed a much stranger reality. The rotation was incredibly complex, and deep inside, they found this sharp, really turbulent layer called the tachocline. This new, messy picture just completely shattered the old theory. The neat, simple mechanism that was supposed to make sunspots drift toward the equator, it just didn't work with this new evidence. Suddenly, the case was wide open again. If the rotation deep down is that complicated, how on Earth could it possibly produce the orderly, predictable march of sunspots we see in every single cycle? The elegant alpha-omega model was in serious trouble. This massive puzzle forced scientists to consider another suspect, a whole competing theory that suggested maybe the main engine of the dynamo wasn't hidden deep inside the sun at all. And this sets up a really fascinating scientific debate. So on one side, you've got the alpha effect, driven by all this small-scale turbulence deep inside the sun. It's a hidden engine. But on the other side, you have the Babcock-Leighton mechanism. And it says, no,
The dynamo engine is right up near the surface, powered by the birth and death of the very sunspots we can actually see. Its engine is observable.
So here's how this surface-level dynamo is supposed to work. Sunspots almost always pop up in pairs, right? But they're usually a little tilted, not perfectly straight. As these super-powerful magnetic regions start to decay, the sun's surface flows act like a giant conveyor belt, pulling one magnetic polarity up towards the poles. Over many years, this process cancels out the old polar field and builds up a brand new one with the opposite charge. And the amazing part is, we can actually watch this happening. So now the mystery has this whole new dimension. Is the dynamo a deep, turbulent process? Is it a visible, surface-level process? Or is it maybe some combination of the two? Scientists are still fiercely debating where the true heart of the dynamo really is. And just when you thought the case couldn't get any more complicated, historical records revealed another baffling behavior. Sometimes, the sun's engine seems to just sputter out, nearly die.
These are the grand minima, these really long periods, sometimes decades, where sunspots almost completely disappear. The most famous one is the Maunder minimum, back in the 17th century. But historical records show these quiet spells are a recurring, if totally unpredictable, part of the sun's long-term behavior.
This adds yet another fundamental question to our investigation. Do these quiet periods mean the entire dynamo process just grinds to a halt? Or is the engine still running, maybe just idling so low that it can't produce the strong magnetic fields you need to make sunspots? Is it off, or is it just being quiet? So, faced with all of these conflicting clues and all these unanswered questions, how are scientists trying to finally crack this century-old case today?
Well, they're turning to one of the most powerful tools in all of modern science, supercomputers. Researchers are now building these huge, incredibly complex numerical models that try to simulate the entire turbulent, rotating, magnetized inside of the sun, basically trying to grow a magnetic cycle from the laws of physics alone. Now, I know this chart looks a little intense, but it tells a really fascinating story. It shows the results from a whole bunch of these supercomputer simulations. Every single dot is one attempt to build a virtual sun. The key takeaway is just how hard it is to get it right. All those red dots in the middle, those represent a stable, sun-like cycle. But look what happens if you just tweak the physics of the simulation a tiny bit. You either get the blue dots, these short, rapid cycles that don't look like our sun at all, or you get absolutely nothing. This extreme sensitivity was a real shock. It showed scientists that the sun's dynamo isn't some robust, unstoppable engine. It's a far more delicate and finely tuned machine than anyone ever imagined.
And solving this really matters. Understanding the dynamo is absolutely crucial for predicting space weather that can knock out our technology. It's also the key to understanding the magnetic activity we see on billions of other stars all across the galaxy. It's a fundamental test of how well we understand physics on a truly cosmic scale. This quote from the scientists behind this research just sums it all up perfectly. We've made incredible progress. We've gone from a simple idea inspired by a car engine all the way to these complex supercomputer models. And yet, it seems like every single answer we find just uncovers a dozen new, even deeper questions.
So yeah, the investigation is far from over. The sun continues to hold its deepest secrets incredibly close. But the search goes on, driven by that relentless curiosity to understand the star that gives us life. The only question left is, what startling new clue will the next generation of observations and simulations finally uncover?